that answer your question? Or?
Yeah, it sounds good. I was just wondering whether you wanted, like, had cares whether they were. I knew the final ones had to be ratio.
Yeah,
but I didn't know.
All the images that you should read to display for the homework should be grayscale.
Okay. Thank you.
Mm-hmm.
Oh, also, and about how long do you think the report should be?
I'm a great believer in Alice. Alice, it's begin at the beginning and right until you come to the end.
Okay.
Page and a half. I mean, a few paragraphs.
Sounds good.
Okay. I don't know where everybody is. I mean, you're all here, but there's a whole lot of people who aren't. Either we've scared some people away or, but I don't know. Anyway, some announcements. A bunch of things about office hours. First of all, the location of the office hours has changed. So I had announced that the daytime office hours of the LAs so these are for the LAs. But their office hours, if it's within 9 to 5, will be in Citizen 282, not 284. 282 is it's this corner of the second floor. Strictly in the corner is a reading room. It's a conference area outside the reading room. Okay. And for those office hours that are after 5 or after, will take place in FB 008, which is just across the corridor here. You can all get into the 0 level after hours, after work hours, and so the FB 008 will allow you access, but you can only get up into the second floor in working hours. Is that clear? Any questions about that? The schedule this week, I've canceled my office hour for tomorrow, but I'm happy to have some office hours today. However, if you want to meet with me today, I need by just after the end of class for you to come up and tell me, right? So I will not necessarily be in my office for the office time or at Zoom for the Zoom time, unless you come up and tell me this class that you want to have a meeting with me, okay? So, but I'm happy to meet with you in person anytime between 11 and 1 in my office in person, which is typically more productive. And if you tell me you want, or virtually today, either between 1 and 3 or between 4 and 5. Okay? You tell me when you beforehand when you're going to come, then I'll be there in my office if it's during that office time, or on Zoom if it's in virtual time. Okay? Mike Jung, one of the LAs, has come down with a fever. He did a COVID test and it's come back inconclusive, so he has to retest. And this is just a warning. He has a fever. He may be beset with COVID-19 infection. If any of you have had contact with him, you should watch yourself for symptoms and get tested if you have some. Questions on anything? I'm going to do a big summary of what we've learned so far and a couple of new things in a moment.
I saw that someone's waiting to,
Oh, thank you. That's a big help. Sorry, Zach, to get you in late. All right. Anyone know how to? Okay. I'm going to do a significant summary of what we've seen so far in terms of basis images. The first basic idea is you start out with an image with m elements. M may be n1 times n2. Does not necessarily have to be the same number in the x direction as in the y, but we're assuming a rectangular image. And for all my examples, I'm assuming n1 equals n2 equals n. Okay, so it's an n by n image. It has m elements, which is n1 times n2, or it may be a three-dimensional image, in which case there are three dimensions, n1 by n2 by n3, in which case capital M is n1 times n2 times n3, or in the case all are the same, n cubed. Okay? So we start off with an image. All these examples are going to be written in terms of 2D images, but I'll say a word about, and they all extend directly to 3D images, and I'll mention how, as we go along, if I fail to remember to say any extension to 3D for you, holler and say, wait, what about 3D? Okay? Okay, so our basic objective is to take this this image with M entries and pixels or voxels, and to write it as a linear combination of basis images. Each one of these psi k's I've underlined to remind you that it's an image, just like I is an image. It has pixels or voxels depending on whether it's 2D or 3D, right, with values in each slot. A sub k, of which there are m, are the coefficients of those basis images. We say we're writing the image as a linear combination of the basis images with coefficients a sub k. Okay? There are multiple possible basis image sets. We've seen 3 of them so far. We're going to see some more. But the 2 that we've been most concerned about are the basis set, the delta k. A delta k, the kth delta image has a 0 everywhere except in the kth pixel, where k is underlined. K, that's in other words, it's a k sub x in the x direction and k sub y in the y direction. Okay? These basis images happen to be orthogonal. What does that mean? We haven't talked about orthogonality. What it means is that when you take the 2 images, in this case delta k and delta j, and you multiply them pixel by pixel, so you get the products in every pixel, and then you sum those products. It's the correspondent to dot product for vectors. Okay? Then you get 0 if k is not equal to j, and non-zero if k is equal to j. Okay? And we call them orthonormal if for k equals to j, that dot product is 1. Okay? The other, okay, in that case, the AK are simply the I sub k. They're just the image pixel value at position k, or voxel value in 3D, at position k in the image. Okay? Question so far? The other important set that we have been talking about are the sinusoids, and I'm writing them in complex form. They're the product of a complex sinusoid in x times of 1 in y, and in 3D you just have a third one, which will be e to the minus I 2 pi kz over n times x. And each one of the n's, if they're not the same n, would be n1, n2, n3 in the respective slots. Okay? And I remind you that each one of these captures a cosine in its real term and a sine at the same frequency in its imaginary term. And these guys I called ky over n. I called the frequency nu sub x, the x frequency, and the y frequency nu sub y. Everybody okay so far? We got sinusoidal basis images. They happen to be complex. Yeah.
Can you drop the equation one more time? I'm not sure I'm reading it correctly.
Can I say again?
The sinusoid, the equation.
It's e to the minus I 2 pi times the frequency k sub x over n times x.
Okay.
And the same thing, but in the case of y over n. Sorry, that's a typo.
Okay.
Y there. E to the minus I 2 pi nu sub y over n y. That do it for you? Sorry.
Yeah, that's what I was reading that in the X. Like, wait, that doesn't seem right. The second one.
Yep. You caught me. Thank you very much for catching me. That's big contribution. Okay. We're going to be interested in algorithms that go from the image to the corresponding set of coefficients. Yeah.
What is the real difference between all of these? Are these just different representations of base image sets? Do they have like different efficiency or something?
What are you asking me to compare?
Like just all of the different things that you have under examples of base image sets?
I have so far I have only 2 examples. So there's no all. There's this one and that.
Oh, okay. I was reading that.
Okay, so this basis set and that basis set. But yes, there are a bunch of other examples, and they all, quote, work, but they differ very much in the computational load to do the things that you want to do, namely to apply operators or to do these transforms that I'm just about to talk about to get the coefficient values from the image values. Okay, does that answer your question?
Yes, sir.
Good. But I'm going to use the word transform as an operator that goes from the image to the corresponding coefficients. And I'm going to use that transform to the -1 as the inverse. That is to say, that goes from the coefficients, a set of coefficients back to the images. Okay? And there's a different transform for each base, for every basis set. We're going to be interested in the sinusoidal basis set, and so we're going to be particularly interested in the transform from I to A and from A to I, from the image to the coefficients, or from the coefficients back to an image, for that particular set. And I've named the transform script F. I know some of you never learned script. I don't know what to say about that, but anyway, I certainly learned script. I'll tell you a very brief story. I was a bright first grader. I could read. And after after a few weeks in first grade, they pushed me up into second grade. And in first grade, they'd learned script. And I didn't know script, right? So second grade teachers, oh, Steve doesn't know script. Dave Skolnick, one of the other second graders, would you please go teach Steve script? So if you can't read my script, it's Dave's fault. And I told him so at our 50th high school reunion. Anyway, okay. But I'm using script F to mean the transform. And in general, in particular, for the transform that we're going to be interested in, we're going from I to these coefficients of the sinusoidal basis images, F for Fourier. Yeah.
Could you explain the orthogonal one again?
Yeah, you take, if you have two images, I and J, and you want to ask whether they're orthogonal, each one is a square, and you just go element by element. So you put the first element here and the first element here and multiply the results. The second element times the second element. Take products, and then so you get the sum of products. Okay, just to say sum of I, K, J, K, summed over K. Okay, summed over the whole image, element by element. Just to remind you, these are just the elements of the images. If that sum is 0 for all basis images, for all images in a set of images, then we say the images are orthogonal. Of course, it's not 0 for K equal to J because you're taking a bunch of sum of squares of non-zero elements. Does that do it for you? Same definition for vectors that if you took some basic linear algebra you learned.
It's just like vectors, but we just have more components now.
Good. Okay. And so it turns out these delta images are orthogonal, but so are the sinusoids. Okay? And I'll tell you why we know that in a minute. Yeah.
Why do we want to know if they're orthogonal?
Because it's going to produce, every one of these properties is going to produce a fast algorithm. This is, after all, an engineering course, a computer science or biomedical engineering course. And so all this math is about getting things that we can do computationally well. And it'll turn out that it is the case that having them be orthogonal makes the F transform faster. Yeah?
What does it say after the basis images with M elements?
What does it say after what?
The basis image with M elements, like
This?
on the right hand side.
This here?
After the two squares, just
I don't know where you're talking about. Examples of basis image sets?
right above that.
This?
Yeah.
Basis images with M elements, values at integer pairs X. In other words, you have pixel values and any XY in 2D or XYZ in 3D. Okay, that do it for you? Sorry, I probably wrote too small, but I filled up the board with with this much. Yeah.
For the sinusoids and the I equals, is that K of X and the K of Y down there? Why is the K of X like a different range? Did you explain that before?
Explain that shortly. It is. The short answer is it's because of the complex conjugacy relations that we talked about last time. Okay? But I'm going to get back to that in a minute. More questions? It's pretty complex, but it's not all that complex if you break it down into these simple pieces. Okay, the next thing is images are things we're going to want to compute on. Right? We're going to want to apply operators. In your homework, you have the first example of such an operator, right? You want to turn an eye image into an edge strength image. That's an operator, the edge strength operator, applied to the input image. Right? And we want the application of those operators to be fast. And the operators we're concerned with largely are linear operators. I've defined what a linear operator is. It says if the input is doubled or tripled or whatever, then the output is doubled, correspondingly doubled or tripled or whatever. And it says if you add two images, you can apply the operator separately to each and then add them, or you can add them and then apply the operator, and it doesn't matter which order you do it. Okay, that's a linear operator. And it turns out that any linear operator on a discrete set of values, which and our images are discrete, we have exactly m discrete elements, it can be written as a multiplication by an m by m matrix. Okay? If it's going to be linear, there is some matrix that corresponds to that operation. But think about what m by m is. M is n squared for a 2D image, and n might be 1,000. So m is 10 to the 6th. And m by m is got 10 to the 12th elements. That multiplication of a 10 to the 6th by 10 to the 6th matrix takes m squared operations. No way we're going to try and ask a computer to do that. It's just not efficient enough. But on the other hand, mathematically, we can take advantage of knowledge that it can be represented by a matrix. And moreover, it can be proven that for shift invariant linear operators, that matrix is symmetric. Okay? So we can take advantage of the properties of eigen images of some operators that can be represented as symmetric. So since for shift invariant linear operators, the matrix is symmetric, its eigenvectors, its eigenimages, are orthogonal. This is just the mathematical argument that says the sinusoidal images that we have, because they are eigenimages of shift invariant linear operators, are going to be orthogonal. And that's going to be helpful in computations, like of script f and f inverse. Okay, so we have these sinusoidal basis images, and we know they're orthogonal. But now comes another property. They are periodic, with period n. Well, some of them have period n over 2, some of them have period n over 3, but if you take two periods of something with n over 2, then you got a period n. The one with n over 3, you take 3 periods of the n over 3 and you get period n. And in general, okay, so the point is every one of them is periodic with period n. Why? Because they're sinusoids, and they're sinusoids with integer values of the k's and integer values of the x's. Okay, the x's are 1, 2, 3. The images get image 1 to n by 1 to n integers, or 0 to n minus 1 by 0 to n minus 1, doesn't matter. Either way, it's periodic with period n. Okay? So all these guys are periodic. So now we have that they're orthogonal. Whoop, left out a word, left out a letter. Orthogonal. And there are they are eigenvectors, the sinusoids of shift invariant linear operators. The fact that they're eigenvectors is going to make applications of operators fast. But it turns out that, double letter here too, ordered. It turns out if you have these orthogonal eigen entities of an operator, eigenimages in our case, they will be ordered by level of detail. And as a result, we can get an efficient summation here. Most of the AKs are going to be, the ones for a very high level of detail are going to all be close to 0. And so we can ignore them. We know and not change the decomposition of the image very much. So if we had only 100 terms, then going from A back to I would be much faster because there are only 100 non-negligible A's. Okay? So they're ordered by level of detail and they're orthogonal. And it turns out that yields a somewhat fast transform from I's to A's or from A's to I's. Somewhat fast means it's order of m squared time, meaning some constant multiple of m squared for large m. Still pretty slow for m equals 10 to the 6th. All right, that's 10 to the 12th operations. Well, that's better than doing it with the matrix, which was 10 to the 12 squared operations, 10 to the 24th. Okay, but it's still, it's still not as fast as we would like. But they have another property. They're separable in x and y. Right? You can write any given basis function as the product of an x basis function and a y basis. An x basis, one-dimensional, the rows, for example, and a y one, the columns. Right? And that, with one other property that I'll mention later that I call multiplicative decomposition, which basically says that if you multiply two exponentials at two different frequencies times each other, you get another one of those exponentials. So you can subdivide them. That yields a very fast transform. That's order m log n. So if you think about log base 2 of 1,000, well, log base 2 of m squared, of log base 2 of what did I say? M is a million. Log base 2 of a million is, log base 2 is 10, 2 times 10, it's 20. So now we're talking about 20 million operations rather than a trillion. to do a square root of f. Right? A lot faster. And it depends on having this orthogonality property, this separability problem, and this multiplicative decomposition property. And that yields an algorithm for root f that's called the fast transform. It doesn't compute anything different. It's just an algorithm for applying script f. It is something, the general algorithm to go from I to A, this f for the sinusoids is called the discrete Fourier transform, DFT. There are lots, I've just told you 3 algorithms for computing them. One is via matrix operations, which is whatever a trillion squared is, 10 to the 24th, if I get it right, yeah, I think so. Anyway, there's the one that only depends on orthogonality, that instead of taking 10 to the 24th, takes only 10 to the 12th. And this guy's going to take 20, say like 20 times million. Okay, so a little more than 10 to the 7th, 2 times 10 to the 7th. Okay, again, notably faster. Its advantage is even greater the bigger m is. So for 3D images, if m is 1,000 by 1,000 by 1,000, now we get 10 to the 9th as m, and the advantage is even greater. And so this algorithm that does this fast f is called the FFT, the fast Fourier transform. Its result is DFT, but it's an algorithm that does it taking advantage of that. For those of you who know what a divide and conquer algorithm, it's a divide and conquer an algorithm, and that's why. And the division and conquering depends on these properties of orthogonality, separability, and so on. Okay? So, any questions?
When you say eigenimages are orthogonal, do you mean every single eigenimage is orthogonal to each other?
Yep.
Everything.
Yes, exactly. That's a striking property, right? You have a whole set of eigenimages. In fact, there are a full n squared of them, a full capital M of them. And each pair, take any pair that's not the same one in both elements of the pair, the sum of products will be 0. Wow.
So,
And that's true. That is a property of eigen entities of symmetric matrices. It doesn't depend. I mean, this is just a special case of that.
are we allowed to say that if our eigenimages are orthogonal, that they have undergone shift invariant operators?
You need to just talk faster. So I have my hearing aids in, and I still not have. Go ahead. The mask is a problem. Go ahead.
If we know that our eigenimages are orthogonal, do we know that it's undergone shift invariant linear operators? Is that what
No, you don't know that. There are other, as long as the matrix operation is symmetric, it's going to work. Yes, for shift invariant linear operators, it is symmetric, but it's not the other way around. It's not necessarily the case just because it's symmetric that it came from a shift invariant linear operator. These matrices that come from shift invariant linear operators are called toplets. Triplets. It's Toeplitz. You'll see that in the literature, and they are not only linear and symmetric, but they also have certain periodic properties. Not too surprising given what's going on here.
Is there a way to visualize the orthogonality of the sinusoidal basis images?
Yeah. Look at the image in the upper left. We're in the upper left panel, and the image in the upper left and the image next down from it. Right? Just this one and this one. And understand that the bright areas are +1 and the dark areas have intensity -1. Well, that's not exactly true because they're sinusoids and but anyway, you have all positive values here that are constant, and you have half positive and half negative values there. And so if you multiply this image times that image, the positive products and the negative products cancel out, right? And likewise, it turns out for this one and this one, right? And so on. The point is you get these positive negatives, and the way the products work, the positive products and the negative products all cancel out when you sum them up. And that's what makes it necessarily sort of going up and down. If it didn't go up and down, it couldn't be orthogonal. Right, because if you had all positives against all positives, for example, or all negatives against all negatives, you wouldn't be able to get 0. Good question, thank you. Keep them up, keep it up. There aren't any bad questions, but there are especially good ones. Okay, the final thing that's special about the sinusoids is the complex conjugacy property, which basically says, for conjugacy, I wrote it down there, but I'm going to rewrite it here. A sub minus k is A sub k star. So if you know the real imaginary parts of A sub k, then all you need to do is to take the negative of the imaginary part, and you know what the coefficients of A sub minus k are. That goes very well with the fact that there are 2 coefficients for every k. Why? Because the exponential has a real and an imaginary part, and so the A sub k's have to be complex as well. They have a real and imaginary part. So one way to think of it is that you have complex A sub k's that have a real part and an imaginary part. Those are two entries per k. If they're going to be 2 entries per k, then we're only going to need m over 2 entries altogether, each with a duple. Right? M over 2 times 2 is m. And we know that we're looking exactly for m coefficients. Okay? Or instead of thinking of them as complex, we can think of them as a magnitude in a phase at every k. Or, if we want, we can also write them as a sine coefficient and a cosine coefficient at that frequency. There are 3 sorts of pairs that you might think of. The people who wrote the FFT algorithm understand it in terms of these complex AKs. But we providing you with an algorithm that transforms the whole business so that it's magnitude and phase. Because the complex ones are hard to think about and magnitude and phase are much easier to think about. So we're providing you with a script F that produces magnitudes and phases, and the homework assignment gives you two programs, two MATLAB programs. One of them, which takes a magnitude and phase and does script F. I'm sorry, takes a image and produces the magnitudes and phases, does script F. And the other, which takes magnitudes and phases and turns it back into an image. You don't need to understand how that algorithm works. You don't even need to call it yourself. You are given, in this assignment, a program that computes partial derivatives. Hey, wait a second, I said you need to be able to take partial derivatives. We spent a bunch of time talking about directional derivatives and how those directional images depend on simple partial derivatives via the tensors. And in particular, edge strength is based on partial derivatives. That partial derivative program that Alan wrote calls these other programs, right? You don't need to know what it's doing yet. Later in the course you will, but I've protected you now from knowing exactly why it does that. By the way, why would you think that derivative calculation, partial derivative calculation, should be done in terms of these basis functions? Basis images. Go ahead. Back in the back.
Well, because they're images themselves, and why would we?
Because they are.
They're images themselves.
No, it has to do with the operator, not with the images. What's the operator? Turn an image into an image. What image are you computing? You start off with an image and you want the partial derivative of that image in, for example, the x direction. That's an operator. It turns an image into an image. What would you guess from what I've told you is the property of that operator? It's shift invariant and linear. So it must be able to be quickly computed using all this mechanism. In fact, you will find shortly that every derivative, no matter what order and no matter what directions, is linear and shift invariant. And so every derivative that we ever want to take, we're going to be doing using this mechanism. Okay, so this picture here is the same as this picture here. It says that we're going to get two of these images. Let me draw it better. Erase this. And in our case, one of them is going to be a magnitude image, and one is going to be a phase image. And at the dots, and at the bars, we don't need phases. We know what the phases are. Yeah.
Could you explain why they're not both invite images because of the conjugacy property?
Yes. Okay. You think this is tough? It's worse because of the periodicity. And here it comes. here is the picture that I had on the previous slide. This one here corresponds to this rectangle here. The frequency, this is the AKs, and it goes from minus n over 2 plus 1 to n over 2 here, and from 0 to n over 2 up here. Okay? But a periodicity by n means that this guy is over here. Also, if you wanted to, you could compute it from 0 to n minus 1 and from 0 to n over 2. And you could take this guy and transplant it over here. Because the value over here by periodicity means exactly the same as over here. And that's unfortunately what the FFT does. It yields you this guy here. So, even though we understand this guy here to be negative frequencies in X, they actually appear here at positive frequencies and beyond. Well, most of the time you will never have to deal with that, but you need, sometime in your future you may need to understand the results of the FFT. Then on top of that, you have complex conjugacy properties, right? So the thing that comes out over here needs to be understood over here, but it's repeated except with a complex conjugate over here. And this guy here is repeated except with changing of the imaginary term, complex conjugacy, changing it to minus its value over here. So when you get this, you have to think of this being transplanted over here, and this being over here, and this being over there. And now I've built up my whole n by n array of coefficients. Positive and negative frequencies both, in both x and y. Is it a mess? Yes, but now you should have the basis for understanding exactly how it goes. Questions? This is something I've already told you, what orthogonality gets you. What orthogonality gets you? Okay, I'm about to erase a lot of the board. Anybody need any of the board? Erase my office hour stuff first. If you have that equation here, I equals AK psi k sums over k. What happens if I take the dot product of this with one of the psi j's, with any of the other, with any particular psi j? Okay? Well, dot product is a linear operator, and so it comes through the multiplication. Like so. I just dot product at anyone with psi j. But wait a second. This dot product is 0 for all k but j. This is a general property of all vector things. An image is R vector type things, but never mind, we're talking about images. So this is 0 if k is not equal to j. Which is another way of saying you get and 1 if k is equal to j, if it's orthonormal. Okay, so says if we have an orthonormal set, they're orthogonal and each individual psi j dotted with itself gives you 1, then all the terms go away but the jth one, and you get aj. There's an algorithm for computing the coefficients. It's a general algorithm. I'm going to jump up and down on you and say this is the dot product algorithm, this is the dot product algorithm, it's the dot product algorithm. It's a big deal. If you have orthogonal bases, then the coefficients can be computed by dot products against the individual basis images. Right? That's why I put an exclamation point there. Okay, and that is the quote fast algorithm, not the it's the fastish algorithm. The one that I said was sort of fast, the dot product algorithm. If you don't have orthogonality, then you have way more operations. But if you have dot product, it's fastish. And if you have all these other properties, you don't do it by dot product. You do it by the FFT, and you get it by that divide and conquer algorithm, even very much faster. Okay, so 3 levels of speed. Orthogonality gives you a notable speed up. The fast one, much more than that. Well, okay, so we need that the dot product each of the psi j's is 1. Well, if we compute these sinusoidal things, and we find out that the sum of the squares of the elements is not 1, that's easy. We take the square root of that sum of squares, and we divide every element by that. And then the sum of the modified elements squared will be 1. So we say we normalize the basis images. And they're still basis images, they're just now normalized basis images. Okay, and for this dot product rule to work, you need normalization, or alternatively, you get that this, or if not normalized, you get aj times psi j dot psi j, and you can compute aj. You can take the result and divide by the dot product of the jth with itself. Okay, fine. We have a dot product algorithm for computing coefficients that simply depends on orthogonality of the basis images. It doesn't depend on them being eigenimages. Doesn't depend on separability. It doesn't depend. It always works as long as you have an orthogonal basis. The separability means that you don't have to do the Fourier transforms of the whole image. You only have to do one-dimensional Fourier transforms of the rows, and then you take the result, and already that's got complex terms in it, each row, and now you're going to but understand that as a new image, which has complex terms in it, and then you're going to take the separability allows you to then take the Fourier transform of the columns. So you really only have to do one-dimensional, many one-dimensional, 2n 2n for a 2D image. If it's 3D, you then have a further result, and you do it on the depth entities. I don't know, there's a row, this column, and there's the thing that's indexed in depth in the image. Anyway, upshot is the separability allows you to do this row by row and column by column, followed by column computation, right? For 2D images. And that's faster too. Questions? Yeah.
Can we represent any image with sinusoidal basis images?
Yes. And you can get its coefficients from that.
So are sinusoidal basis images only really beneficial when you are operating on the image?
Good question. They're especially beneficial when you are going to operate with shift invariant linear operators, because they all have the same basis, same eigenbasis. But even if you're not, the fact that they have this where did I have it here? This guy. The fact that they have this order by level of detail is a big deal all by itself. There are lots of other basis images, however, that satisfy that property and that are even orthogonal. And there's even at least one other pair that I know of that I'm going to tell you in a minute that even has all these other properties of orthogonality and so on, but there just aren't eigenimages of shift invariant linear operators. And so they end up with many of these nice properties, but they miss out the strength in calculating shift invariant linear operators. Why does eigenimages give you the shift invariant linear operator fast? It's because it allows you to go over, compute all the A's. We can do that in m log n time, order m log n time. Then we can multiply element by element by the eigenvalues corresponding to that operator, which turns out to be much faster than applying it directly to the image. You apply the operator in the so-called frequency domain to the coefficients, and then you come back with the inverse f. And it's that way of dealing with things that makes this guy particularly good for applying shift invariant linear operators. But you're right. If they weren't eigenimages, then they would have if they weren't eigenimages, but they were orthogonal, at least you'd be able to do this. But you wouldn't get and you would be able to cut off your series early also. Other questions?
Can you give us an example of a linear operator that is not shift invariant?
Well, one that's not linear is the gradient squared operator, the one you're using here. The gradient is linear, but the gradient squared isn't. Because a squared plus b squared is not the same as a plus b squared. Essentially, that's why. Okay, so there's an example. And so we fight when we want to do the gradient, not to compute the gradient squared, even if we want it. We compute the gradient because it is shift invariant, and then we square the results. We pull out the nonlinearity. Yeah,
What's the relation between the basis?
louder, please.
What's the relation between the basis images and the eigenimages?
The eigenimages are basis images. They're one particular basis. They form a basis. The set of all eigenimages is a particular basis set.
So on that one slide where we have the sine waves visualized as images, those are basis images, and then what would be the eigenimages?
They are the eigenimages.
Is it the same thing?
I'm sorry. A basis set is simply any set psi k that are so-called linearly independent. Okay, but any set psi k will do. That's a basis set. For any given basis set, you have coefficients of that basis set. The sinusoids are one particular basis set of infinitely many possibilities. They are a set of images that form a basis, because there are exactly capital M eigenimages. And they are linearly independent. They're not only linearly independent, they're orthogonal. Does that help?
Yeah, so the eigenimages are like basically the coefficients of the basis images?
No, the coefficient. No. The eigenimages are images. The eigenimages are these guys. The coefficients are these guys.
Thank you.
Given a basis set, whichever image you take in, there will be a corresponding set of coefficients. It's different for different input images. That's what the transform does. It turns your input image into the coefficients. Okay? Good. Okay, so a couple of further things. It's interesting to think about what's going on for these coefficient images, the A's. Okay, so these A's, if they're pasted together like I said here, are an n by n image. And if we look at, and we have a magnitude n by n image and a phase n by n image that we can look at. We can visualize it. We can see what it looks like. But now instead of this being on the left square, this being x and y, that's the input image. It's nu sub x in this direction and nu sub y in that direction. Okay? And so low frequencies are near 0, 0, and higher frequencies as you go out in either x or y. Right? In other words, the sinusoids corresponding to any position in that image near the center are slowly varying a period of the whole of n, or a period of n of a 2 or of n of a 3. And the other ones, the sinusoid is going up and down a lot faster. Right? So you already saw that in this picture here. Right? And if you look here, everything is, the basis images are going from positive to negative very fast. And up here, they're going much slower, from positive to negative. Okay? Anyway, you can visualize those images. And what people normally do is, I guess you're not going to be able to see it on that screen. You're going to have to look at that screen over there because of the way the lights are. But this is the magnitude image that you see on the right. Okay. The interesting thing here is that the dominant direction in the input image is this railroad line, right? And the dominant thing you see in this image is a line in the frequency domain, in the coefficient image, magnitude, which is orthogonal to that guy. And that's, in fact, always the case. If you have dominant vertical thing in your image, you're going to have a horizontal line in that magnitude image. If you have a dominant thing going that way, it's going to be orthogonal in the other image. You're going to see that. The other thing we see, if you look carefully, is it's relatively bright here in the center and dark here, meaning it's got a lot of zero values other than near the low frequencies, near the center of the image. The center is 0, 0 frequency. That's what I promised about cutting off. You will, for essentially every real image, by real I don't mean, sorry, that's a mathematical term, for every everyday image, the one you might take with your camera. Yeah.
So if that edge doesn't go through the origin and the original picture, will it go through the origin?
It doesn't matter where the line is. It will still give you a line and frequency that goes through the origin. Okay, so there are two things that are there in the magnitude image that you can see. And a lot of people love to think in terms of the magnitude images. They're easier to understand. When we think about doing things like smoothing or various other things, we think about what they do on the magnitude. Unfortunately, you will be seriously misled if you ignore the phase image. In fact, if you have to think about what's going on, you should think about the phase image only. The magnitude image is not quite irrelevant, but it's not all that important compared to the phase image. And the reason is, when we look at an image, what are we interested in? We're interested in objects, right? So when I look out here, I see one lovely person next to another lovely person next to another, right? And I'm interested in each of them as individuals. Or I see their noses. Well, I don't see them because they have masks on. Or I see their faces. Or I see their legs. Or whatever. But I'm interested in objects. And the big thing about objects, it's about position in the image. It's not simply about magnitude. It's about where these things are in the image. And just as I said here with regard to the highway the rail line, where it didn't matter where the rail line was, it doesn't affect the magnitude image. It big time affects the phase image, where it is. And so the information about location is in the phase image. Okay? And since we care so much about location, when we analyze images, we're going to be especially concerned with what happens in the phase image. Okay, you asked about other basis function sets. There's a cosine basis set, there's a sine basis set. But two others that are pretty common are the Hadamard set and the Haar set. Okay, they're sets that are previously defined mathematically. These two on the top are sinusoidal. This guy is special because It's a set of orthogonal functions that orthogonal images that only have values +1 or -1. Right? Instead of like the sinusoids that are, have all sorts of values between -1 and +1, a sine or a cosine. These guys have exactly one. And so when you take these, if you want to apply this dot product thing, this dot product of I dot psi j is a sum of ones and -1s, right? You have a 1 and 1, the kth, at some pixel in the kth basis, Hadamard image, and another one in the jth. You're multiplying pixel with 1 times a pixel with either 1 or -1, or 1 with either 1 or, and so you get, upshot is there's no multiplications, there's only additions. It's the sum of products of this dot product. Everything here is multiplied either by a 1 or a -1. So the multiplication is trivial. It's just a sum of a sum of pixel intensity, some of which are multiplied by +1 and some of which are multiplied by -1. So it's even faster. That's great for, oh, by the way, this thing also goes by the name Walsh. You'll also see Walsh. And this even better, these Walsh-Hadamard functions have all the properties you need for the divide and conquer to work. So there is a fast Hadamard algorithm, FHT, and inverse. That's great. Love it. Not eigenimages of shift invariant linear operators. If you want to do shift invariant linear operators, you better use the sinusoidal basis. But if all you want to do is compress the the image to a small number of terms, small non-negligible a sub k's, and then you want to transmit that down the line, the Hadamard is great for that. The properties of these guys, the Haar set, is that the basis functions sort of move around the space. They're at different positions. And that allows you to emphasize position, because if you have zeros everywhere but just a few of these non-zeros, right? So we have 3 colors here, the white and black and gray, and the gray is 0. So it's +1s, -1s, and 0s. But they're localized. And those are going to be pretty good for finding objects because they have that locality property even better than the phase images. Okay, so there are other basis sets that we sometimes are concerned with. And you'll see this guy used for compression and this guy used for image analysis of objects. They all have this nice orthogonality property. They are all defined, typically, the good ones, to be separable. I just said the Hadamard has this multiplicative decomposition on top of the orthogonality that allows you to have a divide and conquer algorithm, a so-called fast algorithm for computing the AKs. But they're not eigenimages of shift invariant linear operators. And so when you want shift invariant linear operators, you better use the sinusoids, the Fourier, the DFT, done by an FFT. The final thing I'm going to say today is that when you apply shift invariant linear operators via the frequency domain, what you're going to get is periodic result. And it's going to be understanding the input as if it were periodic. Because everything's periodic here. And so if you put in a single, here's a lung X-ray, radiographs so-called, you have to think of the input as not being just a lung, but a periodically repeated lung. And so if your operator is going to take derivatives, for example, everywhere in the image, it's also going to take derivatives in these crack areas where there's discontinuous intensities, because the image that's here, values that are here on the left, are also appearing here on the right of the edge, and the same goes from the top to the bottom. And so this wraparound property, the idea that the right continues into the left and the top continues into the bottom, is a problem for the shift invariant linear operators done by in the frequency domain. And so we're going to have to be sensitive to the fact that we can believe these operators in most of this, the result in most of the image area, but by the edges, we're going to have edge effects that are going to corrupt the values near the right edge, the left edge, the top edge, and the bottom edge. Okay, this is a summary that I've already talked about, and I'll repeat next time. This is for the next topic. We are going to now go on to the application of shift invariant linear operators. That's our next topic, right? And shift invariant linear operators can be understood as applying what's called a convolution with a convolution kernel. And we'll see what those are. And we'll see that we will be, because they are shift invariant linear, that they're going to be able to be applied in the frequency domain, but it's going to make us understand better what shift invariant linear operators are. And so that's the next topic. And these references in Birchfield discuss convolution. And in particular, getting derivatives by convolution. Okay, done for today.